have learned that with addition and with addition also you can do multiplication, right? So you know that like repeated addition we can do multiplication. 4 into 5, that means 4 5 times can be addition, right? 4 plus 4 plus 4 plus 4, or 5 4 times. That means adding 5 4 times, 5 plus 5 plus 5 plus 5. So that is a different ways of doing addition or multiplication. Similarly, we can do subtract division using subtraction. That means 10 divided by 2. We go on subtracting 2 from 10 till your the value from which you are subtracting is 0. That means you 10 minus 2, 10 minus 2, 10 minus 2, 10 minus 2, all those things go on till you get a 0. But number of times you are subtracted is your quotient, right? And if the dividend is less than divisor, we we call that is a remainder, right? These things we know already. So the main point is how we are using different resources within the uh, processor to do the common things or to do complicated things. We can use simplified hardware, right? Like that. So today the CPU we'll discuss CPU three components, that is arithmetic logic unit, control unit, and memory unit. So arithmetic logic unit and control unit are the central processing unit. Right? Although you say the processor, that means CPU. These days, as a hardware CPU, we have everything within the motherboard. Even the memory RAM is also in the motherboard, right? Even in the graphics card or any card, sound card or whatever card, it's also in the memory in the motherboard. But here it is a functional division. This kind of a functional division, um, which which tells you what are the functional units in a computer. So ALU and counter unit are considered as functional units in a computer, right? So this is a block diagram which we have discussed in other classes also. So we have a arithmetic logic unit, control unit, and input output unit. So input output unit has also to communicate to CPU, right? And memory unit is kept a bit separate because it needs a lot of size, space, and the time for processing the memory is also bit high, right? So this is also interfaced. So this is a block diagram system. So ALU where data head is held temporarily. All the calculations are done here. All the addition, subtraction, load, store, shift, logical operation, ANDing, ORing, XORing, all those things, ANDing, and this is a calculator. So the data part. So all the data is moved, input, processed, and output through this processing unit. So it's called data part. Okay, especially the arithmetic logic unit is called data path. Control unit we have called control path. Design of control unit is design of control path. So that is definite. Okay. So control unit. So basically, control unit fetches the instruction. It understands. It try to understand what is the instruction. What am I supposed to do? Based on its understanding, it is going to utilize the arithmetic logic unit, the data buses, the input output, etc. So it interprets. Basically, it interprets and controls the execution of instructions. So it needs to know some language. So all this language or instruction which we give to the computer, like adding, storing, multiplication, input, output, faulting, whatever. All this language should be known by the control unit. So control unit is the person who understands, try to understand what am I supposed to do or what the user is trying to do based on the existing hardware. Right? So it interprets and controls, and this control unit responds to the fetch, decode, execute cycle. So corresponds to fetch, decode. So in any time, any random time you take, the processor is always doing three things: fetch, decode, execute. Fetching the instructions, decoding those instructions, and executing those instructions. So this is a cycle: fetch, decode, execute, and continue. Fetch, decode, execute, and go to fetch. Fetch, decode, execute, so on. So this is what you should understand. Now registers. So we have different kinds of memory, but memory is pretty slow. So for real-time processing, to use hard disk or even RAM is going to delay the process. Even RAM is used to even RAM accessing data from the RAM. The processor is going to lose 10 to 15 or even more clock cycles. It has to wait because it is pretty slow, even though it is also placed a bit away from the processor. There's always a lag. So we need some kind of memory within your processor. So that memory is called register, right? So register is a single permanent storage location within CPU and used for particular for a particular or defined purpose, right? Basically, the registers are used for, whenever you're processing data, you need to store it somewhere. The input has to go to the processor. Every time I cannot go to RAM or primary memory and waste even 10 to 15 clock cycles, because processor is going to be idle at that time, going to waste a lot of time. That means your performance is going to degrade by 15 times or 20 times. That is not that's not a good option. So register is like flip flop or even straight register. Sometimes we can use to back converter inverters also, SRAM also. So it's used to hold a binary value temporarily, right, for storage, and it's also for manipulation of a simple calculations, right? So registers have special addresses, so we can name registers anything. They are within the CPU, right? They are the fastest memory. It's much faster than RAM, SRAM, DRAM, whatever, and it is within the processor, and it is very costly also because it takes minimum six transistors to design a SRAM cell. And if you need a flip flop, you need more transistors also. It's very costly also, but very high speed. And it has special addresses, which is named R1, R2, R3, or it can be named, say, T1, T2, whatever. Depends upon the processor. So this is something which I'm introducing to you, Littleman computer. So Littleman computer is, you can say, analogy or a simple description or functional understanding of what the CPU does. So this reference of this material is on your third book. That is, I shared your third book. Mm, I don't remember the author's name, but can refer. That's the second or third chapter of that book. It's Littleman computer. So Littleman is a small person who is living inside a box, you can say CPU. So he has a lot of things like a calculator with him and a mailbox and a reset button, let me say counter, and two baskets. One is for inputting things to the little man, and out basket is we need something from the little man, he gives through the out basket, right? So this is a simplified view. Now let's see a bit more detail about the mailboxes. You can see the mailboxes. How many locations are there in the mailbox? There are only 100 locations. You can see there is start from 000102 to 99. Right, so there are 100 locations. And you can see what is the capacity of the number stored in the little man's mailbox. 100 locations, and each location can store 3 digits. 500199, and they are decimal. You can see the decimal 399 0 to 9. So 3 digits we can store the mailbox. There are 100 such boxes. Now calculator. Calculator also you can see the capacity is 3, 1, 2, 3 digits can be. And whatever Littleman type, it is displayed as any other calculator. Now come back to the in basket out basket. They are just transaction. We can put some Littleman can put some paper after writing something, and I can take to the out basket. If I need to input Littleman something, I write in a paper and put in the in basket. Right. So that's it. Now let's see what the counter. There's a counter just for reference, for a Littleman's reference. You just need to know where it is presently, which instruction it is presently executing, something like this. So we need a counter, and we can say counter has two switches. One switch is with Littleman, and the switch is for the user or the external person who is trying to control the Littleman. So for us, we can press that. We can make it reset. Reset means anything reset, it goes to the initial state, that is 00. So only option with me or the outside person is pressing the reset and making the counter 00. Right? But Littleman has another switch. So when he presses that switch, you can say it will be incremented. The value in the instruction counter is the count will be 1. So it will be counted 1 value. So Littleman can also present. So this is the overall thing. The Littleman calculator mailbox in our basket reset button. So these things are required so that we may understand, we can appreciate in a quick way so that we can even jump to the complex. So all the complex processes can be compared. All the processes existing can be compared to this analogy. There is a person, Littleman, there's a calculator, there's a memory, there is a counter, there's a in and out options. Right. So this is the overall thing. Now these are the instructions. We need arithmetic instructions, and we need data transfer instruction or data movement instructions. It is loading something, storing something, We have to store first, then we have to load it. So like that. Okay, then input and output instructions. After processing, we need to see the output that comes from the output unit. And to add two numbers, we need to input those numbers, have to given to the processor, to the input unit. And stop is break. Right, let's stop, make it stop. Because processor is always fetching, decoding, executing, fetching, decoding, executing. So we cannot stop it basically. The only way to stop it is we'll make sure that the instruction which we are giving to it is stop instruction. That means it says there is nothing to do. That means no data movement, nothing. So that also is instruction stop. Now to stop, we have to give an instruction. So we should know the process is always doing something, fetching, decoding, executing, fetching, decoding. To make it stop, we should give an instruction like stop. So it going on stopping. It start executing the instruction stop, again stop, something like that. So it is always doing fetching, decoding, execution. So any processor, any complicated processor nowadays also, even i7, i3, x86, AMD or Motorola, any company you take any processor, you'll have this basic instructions from arithmetic. Although these days we have very complicated instructions like squaring, logarithm, exponential, all those things. But for simplicity, we are taking two instructions for arithmetic: data transfer, also load and store, and input output also and stuff. And you can see there is a label to each of these instructions. Arithmetic instruction add have the label or instruction 1xx. So whenever little man see 1, it knows it is addition. So this is the code. We can say the instruction set. This is called instruction set. Each of these numerical codes is used to simplify the instruction. I don't want to write add input or every time. So I'll make a small code using an encoder or something. So this is the code for add instruction. The code is 1, and XX it denotes the memory location, right? So whenever see 1, little man understand it's adding. So XX means I have to take something from memory for adding. That means, and that value which is to be added is stored in XX, right? So you may think that there should be two values, right? So one value by default is already in the calculator screen. That's very important. So one value is in the calculator screen. You need to add another value from the location XX, right? So it goes to the gentleman, go to the XX location, take that value, write it down in a paper, and come back to the calculator screen. Then there is some already value in the calculator screen, and gentleman presses the button plus, that means in the calculator, then it writes the number which is already stored in the memory location x, right? Then he presses equal to, so we get the result in the calculator screen, right? That's add. Subtraction also similarly, whenever little man sees 2, it knows it is subtraction. And subtraction what to what, the number, this number already in the calculator screen, that number, from that number, and I need to subtract the number stored in XX location. So let go to the XX location, write it down that number in a sheet of paper, and come back to the calculator screen, press minus, and type the number in the XX location, and press equal to. So I'll get the first. So that's it. So data moment is also store and load. So 3 stands for store, 5 stands for load. So we always need a location. We always need a location when you are doing a data transfer. So three means from the calculator screen. Sorry, store means from the calculator screen I need to put into the mailbox in the memory. So whenever let says 3, it takes that value in the calculator screen and write it in a piece of paper and stores it in the location exit. Load is just opposite. So its code is 5. So whenever letterman sees the 5, number 5, he know that it's load, right? So it just takes the number, the location XX, write in a sheet of paper, and come and type in the calculator screen. So that is loading something from the memory. So always know that loading from the memory, storing into the memory, right? So loading means from the mailbox or memory to the calculator screen, right? To the execution unit, and storing means from the calculator screen, from the execution data path to the memory. Right? So input output and 0 1. We don't need a memory operation. So whatever in the calculator screen is put into the out basket using output 902. Input, if you give 901, letterman will come to the in basket and it collects those sheet of paper which is put in the in basket and types in the calculator screen. So that's it. The different instructions. Stop means we'll take a break. So access means the memory location. Right? Access means memory location. Okay. So as I discussed, these are the different instructions. Load instruction, this is output 5. So as I discussed, whenever load instruction, something has to be taken from the memory. So what does the Redman do? Redman goes to the mailbox to specified location XX. We have to specify the XX. So that specified XX location in the memory, Redman goes to that location and reads the 3-digit number in that mailbox and puts into the calculator. Right. So the main important thing is the number is not changed in the memory. So we should not use non-destructive reading. When we read something from memory, it should not get destroyed. The charge or should remain. So it is non-destructive read. So the number in the mailbox is unchanged, right? And there will be always another number in the calculator screen that is overwritten. The number in the existing number in the calculator screen is replaced by the new number in the location access, right? So there is a opcode. What does it mean by opcode? Opcode means operation code. It's the instruction code. So every instruction is telling your processor to do something. So that's the operation code. Operation code. Now another word you may also come across is operand. So operand means data on which your opcode is working. That means your add. Add is the opcode, operation code, but operand is add what? A and B. So they are operands. Like this. So this is a term for. Now we have store instruction. Similarly, store instruction is opposite of load instruction. So we can see that whenever store instruction is written, the manual takes that number which is written in the calculator screen and goes to the mailbox and puts that in the location access. So the main important thing is number in the calculator screen does not change. That is, it's non-destructive read, which is Redman is doing. Because it's just taking a piece of paper and copying. It's basically like copying. It's not cutting. Okay. Number in the mailbox is replaced with a new value, right? So the memory is replaced because we are overwriting it. Now, add instruction is also similar. Even add instruction, we know that there is some memory location within the instruction, 1 and XX, right? So the Littleman walks out to the mailbox, the address specified in the instruction after 1 XX. In that location XX, he reads the number in that location XX and come to the calculator and add this number to the number already in the calculator screen, right? So the main thing is number in the mailbox is unchanged. And now subtraction is similarly, the only thing is the operation is changing to minus. Now input output, this is simple. Gentlemen, get a slip of paper from the in basket if the instruction is input. Then he types this number into the calculator screen. If input instruction handles only one slip of paper, yeah, at a time we can take only slip of paper with the 3-digit numbers written because the calculator capacity is also 3 digit. For simplicity, we are taking everything very simple, not any complicated. So there is no address portion in this input read because it is just telling measurement to go to the in basket or reverse. Right? So this is no address location. Right. So and the that out instruction of print is also similar. Whatever in the calculator screen, the man will take that, copy that thing and put in the out basket. Okay, it is also non-destructive. Here also the calculator values remains unchanged. This also doesn't have any instruction or memory location in this instruction. So I don't need to worry about the 90202 point. Maybe I can put this 9 and the input I can give some other value like 6 or something. Also fine. So other thing 02 is don't care actually because input is 01, output is 02. That's the only thing. Okay, once again, we'll refresh the instruction that is adding, subtracting, storing, loading, input, output, and stuff. So any processor have these 5, at least this 4 group of instructions: arithmetic, data transfer, input, output, and machine control, stop, start, right? All those things. So we can see the top right portion. This is the you can say mnemonic, the way we write assignment. Calculator assigned as calculator plus x, that's addition. Calculator assigned as calculator minus x. And directly writing calculator into memory is storing, and putting the value from the memory into calculator screen is loading, and input basket to calculator screen is input, or to calculator screen to output is output. So these are the different instructions. So break is little man takes a break, it does nothing. So he ignores the address portion here also. It's a machine control. Stops the operation. That's it. Simple operation. So we'll just discuss some simple management code so that we'll understand how to write a simple assembly code. Then we'll go to complicated operations and explore some other important instruction which is required in this process to execute complex operations. Okay, so right now this thing we need some a method to tell the determinant where to find the particular instruction. Determinant has very less memory, so it has to guide it where it need to execute. So all these instructions which we are giving to determinant will be already stored in the mailbox, right? So or whatever you need to tell determinant, it has to be stored in the mailbox only. So your instructions to the little man is also stored in the mailbox, and data used by the little man or by the input to the little man by the user is also stored in the mailbox. So mailbox is kind of a only option of memory. So all those things, so instructions or programs as well as data has to be put into your mailbox. So little man also needs to also find a way which location I have to execute right now. So we need one more option like instruction counter that we will discuss. So all these instructions are stored in mailbox and starting location is 00. So Littleman will perform instruction looking at the value in the instruction counter. Okay, instruction location counter. So we need Littleman needs the guidance. How many lines or where I have already, which instructions I have already executed, which instruction I have to execute next, like that. So we need a counter for its internal use. It's called instruction location counter. So that it can every time it finishes a instruction execution, it just presses those counter, and now it know I need to process the next instruction, which is shown in the counter. So those locations indicates or give settlement to go to the mailbox in that location and fetch the next instruction. Okay, so each time Littleman completes instruction, he will increment the instruction location counter, and he has one switch with him, so he can increment it. And then after incrementing, it reads the location or the value in the instruction counter, and it goes to that specified location in the mailbox, so that we can get the next instruction. Okay, so let's take an example of adding two numbers. It is more simplicity. And the output should be given to the user through the outpass. Input should also be taken from the user from the in basket. So this first instruction input 901. So whenever we give this instruction, Littleman is ready. He knows that some input is going to come to the in basket. So it waits near the in basket. So then what it does, store. Then we give the instruction store 99. So this code is 399, right? Store 99 is what I want Littleman to do. So what is 99 here? XX, that's location in the memory. What I need in that location memory, I need to store something. What I need to store? I need to store the value input. So one more thing here, in the input instruction, Littleman will take whatever number input to the in basket and types in the calculator screen. That is very important. It takes the number, it writes it, copy it in its own notebook or something, and come back to the calculator and write those number which we have inputted into the calculator screen. There completes the instruction input. Right, from the fetching the input data or the number from the in basket, carrying into the calculator screen and writing that number in the calculator screen only completes the input instruction. Now once the number is in the calculator screen, now I am calling the instruction store. So what happens? Code is 399. Littleman will note that number in the calculator screen, and it goes to say location in the mailbox. Which location? 99 location, and it stores that value in the in the calculator screen and write in a piece of paper and stores in the location 99. So that's completes the store instruction. Okay. So initially, if you have two input, there is no meaning. If two instructions are input and input, because input is writing into the calculator screen. Again, if I call input, again the new number will be the second number I need to add will be again overwritten by the first number will be overwritten by second number. So before overwriting your calculator screen, you have to store it in the mailbox. So that's why I'm not inputting together input, right? Input first number, input second number. So before inputting second number, I need to store the first number. So after input instruction, I need to store the first number to some location like 99, last location. So you can see why I'm storing in 99 location, because that's my last location. So I know all this instruction which is given to the little man has to be stored somewhere. That I'll start from 00, 01, 02, 03 from this top of the memory. And all those data transfer or data storing, I'll be using the bottom part of my mailbox. You can see how a program, how Littleman is or controlling, or how the unit is managing the memory. If you use same portion from the top for instruction and data, it'll be overwriting the instruction and it'll stuck. Your instruction machine will get stuck. You can see this is usually done by the viruses. They uses the storing area, buffer area, and either this changes location or the instruction counter or pointing to the buffer area, or it changes the instruction which has to be read into some other instruction, overwriting the buffer area so that your program or your operating system is going to execute something else for a virus or Trojan kind of thing. So like that. So then what next instruction input is second number. Now the second number is typed in the calculator screen. Now I can, first number is already in the calculator screen. Second number is, sorry, first number is already stored in location 99. Second number is already in the calculator screen. Now we can execute the instruction add 99. Okay, so add 99 means what? The second number is already in the calculator screen. So the first number is from the location 99 is taken by the little man, and little man fetches that number, come back to the calculator screen, presses the button plus in the calculator, and adds the second first number which is stored in 99. Now each process equal to the number is displayed in the calculator screen. Then the number already displayed in the calculator screen can be output to the user if you give an instruction output. Littleman will put the result in the out basket. So we got the result. Now whatever instruction we need has been executed, we can stop. So it's a break. Let's break the functioning of the. Okay, so all this instruction has to be sequentially stored in the mailbox. I already discussed, we'll store it from the location 00, 01, 02 and so on. Okay, so again, if we reset the location or the instruction counter, again Littleman is going to execute all this instruction again. Okay. So again, let's refresh again. This is very important. 4 instructions that is the most important part of any processor. Which like a lot of instructions are there. Most probably the hardware for that is embedded within the processor. So processor is capable of executing this. Okay, so this is our program. So we know what are we trying to do using the top right portion, input, store 99, again input, add 99, again output and stop. This is the complete assembly language program for the Littleman computer. So corresponding code you may look like this, the mailbox code. So when you have to store something, um, so this is the so these are the location in the mailbox. 00 location I'm storing 901, and 01 location again 399, that is storing, again inputting 901, again now I can add the second number with the first number, again output and stop. So this is the complete instruction code. So this is simplification. All the instruction I can simplify into assembly code. This is called assembly code. All the processor created will have an assembly code. The assembly language programming, which is more difficult than other language programming because you need a lot of understanding of the hardware also for efficient programming. So right now we use C, CPP, Java, Python for these things, which doesn't require any understanding about the hardware. But assembly provides the most optimal or more efficient coding in assembly language coding, right? Because you are working on the top of hardware, you know what is hardware doing. So rather than a automated systems or a software doing the assembly code conversion, if you are able to do it nicely, it is much better, much efficient in terms of frequency, power consumption, even area. of the code, optimization of the memory, etc. Okay, so we have simulator. I will share you the simulator code. An app is also there. So let's write a program to add three numbers. We have done adding two numbers. We need to so basically this is overall thing. What is this meaning of this? Your determine is actually a control unit, and ALU is a calculator ALU. The input output interface is your baskets. The program counter or instruction counter is something with the hardware register, which is already the counter, which is already the CPU, which is guiding the CPU. Where is my next instruction coming from? Where am I? How much to go, etc. Like a map. Memory, the mailbox response memory. Okay, so Littleman computer is simple model, so we can give more features to Littleman and extend this to. So all those lot of things cannot be done using Littleman because we don't have branching instructions, right? So we have limited memory, limited storage, everything is limited, but it represents the any processor. So Letterman basically it has a branching instruction also, without which we cannot do much things. We cannot do multiplication, division, etc. So branching is also required. So Letterman also has some branching instruction. 6xx branch unconditionally. Branch unconditionally means when I see this instruction, I'm going to jump the program code from any location to another location, not in a sequential manner. I'm not following instruction counter right now. I'll be jumping. So 6xx branch unconditionally, jump to location x. Another instruction is 7xx. That is also branching. That is a conditional branch. What is a conditional branch? Whenever the value in the calculator screen is 0, now I'm jumping to location xx, like conditional. If, else, while, for, like all those are conditional branch. So branch on 0. Another is branch on positive. Whenever the value in the calculator screen is positive, now I'm going to jump. That is 8. Upward is 8. So which location I'm going to jump? That is given by xx. Right? 8 followed by xx means if the value in the calculator screen is positive, I need to go to location x. So there are three branch instructions for the time being. And it makes a lot of things can be done using now this thing. So there's an app. You can if someone don't have a laptop or anything, they can download an app. Middleman Computer, which is LMC. I may share in this group or maybe in this classroom. So this is so they can try little different programs. You can make your own ideas, logicals, all those. So this is how it works. There's memory, location, mailbox, a calculator screen, program counter, everything. Whatever we discuss will be in that app, and you can try different programs. You need some patience to understand that. Not difficult. So if someone is interested in directly going to laptop, we can directly go to this website and you can see this Redmond computer in action. It also shows you how it is working in real time. What are the things, program counter changing, data is going here and there. There are 100 locations. All those things, whatever we discussed, is in this website, LNC. And Lindemann is very famous. You can learn a lot of materials in LNC and a lot of program can directly apps you can get in your PC also. It is more friendly. This may look like complicated, but there are much simple apps available also. Feature. There are other challenges we can try adding three or four numbers. From right now, you can try three numbers, then four numbers. Then you can try multiplication, but you need branching instructions and division. So you can try using subtraction and power of two raised to one, two raised to two, three, four. You can try that also. Fibonacci series also you can try. That's also challenging. It's good exercise. So first of sum of n natural numbers using LMC, sum of first even numbers, odd numbers, multiples of n. All those can be done. These are simple challenges. More advanced challenges are also there, which we will discuss later. So this is Year of Englander. This is the book which I shared in the third as a third reference. So all those things which we discussed is from this third chapter or second chapter, I think. Mostly third chapter. Okay. So the book's name is Architecture of Computer Hardware Systems, Software and Networking, Information Technology Approach. Building. Okay. So there are some challenges for Littleman. You can go to futurelearn.com. So this you will get some more challenging exercises. So that's all from my part. So any questions you can ask? If there's any questions you can take, else you can put your roll number. So you can try. There is some challenging. You can start with simple things, then you can go for complicated things. Okay, so that so I'll stop recording.